Welcome to week 6 of the tutorial session of the course Control Systems by Professor C.S. Shankar Ram. So today we will be discussing questions on steady state error, and second will be questions on root locus. And I hope you all have gone through the lectures that are uploaded in the NPTEL by Professor. We'll start with a revision type of question where we are given a second order plant whose dynamics is y double dot plus 4y dot equals to ut, and we need to design a unity negative feedback closed loop control system using a proportional controller. Then for stability, what should be the value of k, or what should be the range of k? For such problems, we know that the open loop transfer function will be equal to, since we are using a proportional controller, so it will be kp divided by s square plus 4s. Right. Now, if we find the closed loop transfer function, which will be g by 1 plus gh, and since h equals to 1, because we are using a unity feedback, therefore our closed loop transfer function will be kp divided by s square plus 4s plus kp. Now, in order to have stable closed loop system, we need to have all the poles should lie on the left half plane of the S plane. So for that we need to solve the characteristic equation, which is s square plus 4s plus kp equals to 0. And for this to have roots to lie on the LHP, what we need all the coefficients should be non-zero and there should be no sign change. Therefore kp should be greater than 0. Okay, so the correct option is option 3. For this problem that we have just solved, whose open loop transfer function was kp divided by s square plus 4s, you need to find out which type of system this is. Okay, whether it is type 0, type 1, type 2 or type 3. This is very simple because we know the type of system is nothing but the number of open loop poles at the origin. So this we can write as s plus 4. Since only one s we can extract from the denominator, so there are only one open loop pole at the origin, therefore it is a type 1 system. Okay, for this problem, we need to find out the static position error constant for problem 1. So, problem 1 has the open loop transfer function as Kp divided by s square plus 4s. So, for this one, we need to find out the static position error constant. As per the definition of static position error constant, we know the position error constant, that we denote it as KPE, is nothing but limit s tends to 0 open loop transfer function. Okay, so we have GH given as Kp divided by s square plus 4s, so it is limit s tends to 0 Kp divided by s square plus 4s. Now if we put s equals to 0, this term will tend to infinity. Therefore, we have the static error constant in this case will be infinity. For the above problem, which has the open loop transfer function as Kp divided by s square plus 4s, we need to find out the steady state tracking error when we have provided a unit step reference input. So the input R is 1 by s, that is unit step. What will be the steady state tracking error? Okay, just now we have calculated the static position error constant in the previous question, which was KPE was infinity. Okay, now as per definition, the steady state error is nothing but 1 divided by 1 plus KPE. So if we put Kp equals to infinity, this will be 0. So in this case, the steady state tracking error will be 0. Now similarly in this question, the input is now a unit ramp input. What will be the steady state tracking error in this case? Let me write the open loop transfer function. GH is Kp by square plus 4s. Try it first, then I will solve it. Okay, so for this problem, the input is a unit ramp input. Okay, so earlier we have the step input, so we calculated the static error constant. Then in the case of ramp input, we need to find out the velocity error constant, which is nothing but limit s tends to 0 s into gh. So if we solve it, we will get s into kp divided by, if we take s common from the denominator, it will be s plus 4, and if we put s equals to 0, it will be kp divided by 4. Okay, and as per definition, steady state error is nothing but 1 divided by kVe, which is 4 by kp. So the correct option is third. Another way to solve this question is to go without using formula. We know that steady state error is nothing but limit s tends to 0 s rs divided by 1 plus gh. Now since r of s is ramp, so it is 1 by s square. So if we put it here, it will be 1 by s, and 1 plus gh will be s square plus 4s kp divided by s square plus 4s. So s will cancel out, will be left with, and s tends to 0 will give us 4 divided by kp. We will get the same answer. So we can solve it either way, using the basic concept or using the formula. Okay, then similar way we need to find out the static acceleration error constant, where we have the open loop transfer function given as kp divided by s square plus 4s. Okay, as per the definition, we know that the acceleration error constant, if we denote it as KAE, it is nothing but limit s tends to 0 s square into open loop transfer function, that is GH. Then it will be kp divided by s square plus 4s. 1s will cancel out, so we'll be left with s times of kp and divided by s plus 4. So if we put s equals to 0, this will be 0. Okay, in this question we are given the open loop transfer function, which is 4s plus 2 divided by s square minus s. Okay, so the open loop transfer function of a unity negative feedback control system is given. For s equals to minus 2, we need to find out whether it satisfies the magnitude and angle condition that is there in the root locus. Okay, so before solving this question, we must know what does it mean by magnitude condition and angle condition. So for root locus, we are solving, we are basically plotting the closed loop poles of a system by varying the gain k. Okay, so the poles will lie on the root locus if it satisfies gh equals to minus 1. That means the magnitude of gh is 1 and the angle of gh for the pole s should be odd multiple of 180 degree. Okay, so how to check these two conditions? So the pole to lie on the root locus, it should satisfy the magnitude criteria, that is for the given s in this question, that is s equals to minus 2, it should have magnitude of open loop transfer function equals to 1 and the angle should be odd multiple of plus minus 180 degrees. Okay, before that let's plot the poles and zeros of the system. So from here we know that the zeros of the open loop transfer function, let's write it down. 0 of open loop transfer function is at minus 1 by 2 and poles of open loop transfer function is at 0 and 1. So we have 2 poles and 1 zeros of the open loop transfer function. So it will be lying at minus 1 by 2. This is the pole 0 and pole 1. Okay. Okay, in the GH, which is given as 4s plus 2 divided by s square minus s, if we put s equals to 2, what we will get? No, we have to calculate at minus 2. So it will be minus 8 plus 2 will be minus 6 and 2 square 4 and minus plus 2, it will be minus 6 by 6, which is minus 1. Okay, Now if we find out its magnitude, it will be 1. So it satisfies the magnitude criteria. Now for the next part, whether it satisfies the angle condition or not. Now in the S plane, if we see, S equals to -2 will be here. Okay, what will be the angle contribution? How to check this angle condition? We okay, what will be the angle of GH at S equals to -2? So it will be nothing but angle of, which is, if I can write it as minus, since it is in denominator, angle of S and minus angle of, it is 1 at S equals to -2. Okay, so angle contribution of 0 minus the angle contribution of pole. So from the S plane, we can see that we have 0 at -1/2. So this angle will be nothing but 180 degrees from the x-axis. This vector is having the angle of 180 degrees. And from 0, again we have the angle of 180 degrees. Okay. And from 1, also we have the angle of 180 degrees. So the net angle contribution is -180 degrees, which is the odd multiple of the angle criteria. Therefore, it satisfies the angle criteria as well. The correct option will be both the magnitude condition and the angle condition. Okay. The next question says that the open loop transfer function of a negative feedback closed loop system is given as k by s cube plus 4s square plus 8s. We are given the open loop transfer function, which is k divided by s cube plus 4s square plus 8s, where k is non-negative real valued parameter. Then we have to find out the true statement. We are given the open loop transfer function and we have to identify the number of branches and where they are terminating to. So first find out how many branches are there in this system. How many branches will be there in the root locus for this open loop transfer function. we know number of branches in root locus is nothing but the number of poles of open loop transfer function. In this case, number of poles are 3, so there will be altogether 4 branches. Okay, because we know that the root locus starts from the open loop poles of the open loop transfer function, and that is why the number of poles equals the number of branches. And the second part is asking about out of these 3, where would these terminate? Okay, are there any zeros in the open loop transfer function? Since there are no zeros, then we know that the root locus terminates at the open loop zeros, but there are no zeros. Then where would these branches terminate? Since there are no zeros in the open loop transfer function, we know in that case the branch will terminate to infinity along the asymptotes. Okay, there will be asymptotes, and it will go to infinity along the asymptotes. So option number 2 is the correct one. For this problem, with open loop transfer function given as k by s cube plus 4s square plus 8s, we need to find out the complex conjugate open loop poles. So we need to find out nothing but the poles of the open loop transfer function. Okay, so this is very simple. We need to just solve this to 0. So one pole will be at 0 and the other will be complex. To find the complex one, we need to solve this one. Okay, from here we can find out s equals to minus 4 plus minus under root b square minus 4ac will be 60 minus 32 by 2, which is equal to 4i divided by 2. So it will be minus 2 plus minus, let's say j, 2j. So the option number 4 is the correct one. Okay, again for the same problem with open loop transfer function equals to k divided by s cube plus 4s square plus 8s. Find out the region of the real axis that lies on the root locus. Just now we have calculated the open loop poles of this system, which so one was at 0, another one was conjugate, and on the LHP, that is -2 -2j and -2 plus 2j. So if we see, sorry, if we see the root locus, not the root locus, but so the poles are at 0, -2 plus 2j and -2 -2j. Okay, so the question is, where will, which region of real axis will lie on the root locus? So we know the real axis to lie on the root locus, the total number of poles and zeros of open loop transfer function to the right of that region should be odd. With this condition, if we see, if we start from -infinity to this one, this region, we can easily see that the right of this region have total 3 poles, which is odd. So this region is going to, or not the region, but this part of real axis will going to lie on the root locus. Okay, and what about this region? So for this region also, the number of poles, in this case we have only poles, is 1, which is odd. Then what will be the region of real axis on the root locus? This odd region will lie, that is -infinity to 0. Okay, so for the previous question, what will be the number of asymptotes? Number of asymptotes is nothing but number of open loop poles minus number of open loop zeros. So in our case there are no zeros and total number of open loop poles were 3. So the total number of asymptotes will be 3. Very simple one. What are the angles made by the asymptotes with the positive real axis? So we have 3 asymptotes, and for each one we need to find out the angle it will make with the positive real axis. Option 2. Okay, let's solve it. So we know that the angle made by asymptotes is equal to 180 2k plus 1 divided by n minus m, where n is the number of open loop poles and m is the number of open loop zeros. So for our case it is 180 divided by 3, that is the odd multiples of 60 degree. So for k0 we will get 60, for k1 we will get 180, and for k equals to 2 we will get 300 degree. Okay, the option 2 will be correct. So if we want to visualize it on the root locus, since we have roots at these locations, the asymptotes will intersect at some point. We don't know the point, but it will have maybe 60 degree, 300 degree and 180 degree. The asymptotes will have this type of nature. Okay, the obvious question, what will be the point of intersection of these asymptotes? Where would they intersect the real axis? Okay. Okay, my connection. Yes. The point of intersection of the asymptotes. Again, this is formula based question. So point of intersection of asymptotes is equal to, we have to calculate the sum of poles and subtract from it the sum of zeros and then divide it with the number of poles minus number of zeros. This will give us the coordinate of the point of intersection of asymptotes. In our case, the poles were 0 and then -2 plus 2j and then -2 minus 2j, and there was 0, no zeros were there. something we need to subtract, divided by 3. So this will give us minus 4 by 3, okay, which is minus 1.33. So this point will be minus 1.33 comma 0. In this question, which option is correct regarding break-in or breakaway point? Before that, we first need to find out whether there is any break-in or breakaway point in the system or not. And if that is present, where what is its coordinate? So first we need to find out if there are any breakaway or break-in points. Option number 4. Okay, let's find out. So first let's draw our poles. Okay. Now from here we can see there are no consecutive poles or consecutive 0, but with this we cannot conclude that there will be no breakaway or break-in point. So we need to solve the condition where we first write the open loop pole JGH, which is K divided by SQ plus 4S square plus 8S. Okay, and we need to write it like this, the form of numerator or denominator. So numerator is, so AS will be nothing but 1 and BS will be nothing but SQ plus 4S square plus 8S, and then we need to solve B dash A minus A dash B equals to 0, because at the break-in or breakaway point this condition is satisfied. So what will be B dash A? It will be the derivative of PS with respect to S, which is 3S square plus 8S plus 8. And what will be A dash S? It is constant, so 0. Now from here we have B dash A will be nothing but 3S square plus 8S plus 8, and since A dash is 0, this is equals to 0. Okay, For this, if we find s, it will be minus 8 plus minus under root b square minus 4ac 32 to 6 and divided by 6. Okay, so this will be minus 8 plus minus something, some value will be there. It will be 2 and 3 divided by 6j. Okay, so some s we are getting, and first of all this s is imaginary. Okay, even though it is there, if we find k which is minus p by a at that s, it should come positive. Now if you solve this, you will get 0, because this is nothing but the root of this only, and a is 1, so it will be 0, which is not greater than 0, because k should be greater than 0 here. So that means there are no breakaway or break-in points. Okay, now the question is, the closed loop system would be stable for all positive. Okay, with open loop transfer function given as kp divided by, it was s cube 4s square plus 8s. Yes. What will be the range of k for the closed loop system to be stable? Since this is a cubic polynomial, we cannot use the condition all coefficients non-zero and no sign change. That is valid for second order polynomial only, till second order polynomial. So for third order, we need to solve it using the Routh-Hurwitz criteria. Therefore, we need to calculate the Routh table. Okay, so first write the characteristic equation of the closed loop transfer function, which is nothing but s cube plus 4s square plus 8s plus kp. So for s cube, it will be 1, 8. For s square, it is 4 and kp. And for s, we need to multiply these two and divide with this, so it is 32 minus kp divided by 4, and this term will be 0. For s0, we will have this term divided by this term, so it is kp only. Now as per route array, all the poles will lie on LHP if there are no sign change. So there are no sign change here, and in order to ensure there are no sign change in this step, we need to ensure 32 minus kp by 4 is greater than 0, and further also for no sign change in this step, kp should be greater than 0 also. So from these two conditions, please find out the range of k or kp for the closed loop stability. Okay, if we solve it, we get 32 minus kp greater than 0. That means kp should be less than 32. And the second condition gives us kp should be greater than 0. That is what we are solving for positive gains we are solving. So kp should be less than 32. The correct option is A. Okay, now let's solve some other problems. Okay. So we are given the root locus of a third order system. So there is a third order system whose root locus is like this. This is 1, 2. This point is root 3, 2 root 3. Similarly, minus root 3, minus 2 root 3. This is minus 1, this is minus 2, this is minus 3. We need to find out open loop transfer function. What will be the open loop transfer function of this system whose root locus is provided? Okay. From the root locus, what we are seeing is there are 3 branches coming out from the origin. Okay, I have missed the arrow. And these branches are terminating to infinity, right? So what can we conclude from here? So there are three branches, means there are three open loop poles. Okay, and all are originating from the origin. So all these poles are at the origin, and all these three branches are terminating to infinity along the asymptotes. So there are no open loop zeros in the system because none of the branches are terminating to any finite value. Okay, so what would be the the open loop transfer function in this case? So from the root locus we can conclude that open loop poles, number of open loop poles equals to 3 because we have 3 branches, and the location is at the origin because our root locus starts from the open loop poles. Okay, so, and since there are no zeros, so we can conclude that the open loop transfer function is nothing but k by sq. Okay, so this is the open loop transfer function for the given root locus. Let's do some more problems. So in the next problem which is given to us, we have a transfer function which is k s square minus 4s plus 20 divided by s plus 2 and s plus 4, and this is closed with a unity negative feedback with input r. For this system, find number of branches or starting points, ending points, and number of asymptotes. What are the number of branches, starting points, ending points, and number of asymptotes of the root locus? Okay, from the block diagram, we are provided with nothing but the open loop transfer function. Okay, the open loop transfer function is k square minus 4s plus 20 divided by s plus 2 and s plus 4. Okay, we know that the number of open loop poles equals to the number of branches, which in this case is 2 because we have 2 poles, so there are 2 branches. And the second one is, what are the starting point from where the root locus will start? We know that the root locus starts from the open loop poles. Okay, So the open loop poles are located at s equals to -2 and s equals to -4. So the starting point will be -2 and -4. What are the ending points? We know that the root locus ends at the um, open loop zeros. Now we have two branches, okay, and also we have two zeros, okay. So these two branches will terminate at these two zeros, okay. So that's why in this case the ending points will be the zeros of the open loop transfer function, and the zeros are located at, we can calculate it by solving this polynomial, and if we solve it, what points we will get? S equals to divided by 2. Okay, so it is 4, 6, 2 plus minus 4j. The zeros are complex and it occurs in conjugate at 2 plus 4j and 2 minus 4j. So our root locus will terminate at this point. And what are the number of asymptotes? So number of asymptotes is nothing but number of poles minus number of zeros, which in this case is 2 minus 2, which is 0, because we have equal number of zeros and equal number of poles. Okay. Solve another question. Find centroid asymptotes for the open loop transfer function given as k s plus 1 divided by s into s plus 2 and s plus 3. Find the centroid of asymptotes, that is the point where the asymptotes meet. For that, first we need to calculate the open loop poles, and it is easy to calculate. So the poles are at 0, -2 and -3. Similarly, the open loop zeros are at -1, and the centroid is nothing but sum of poles minus sum of zeros divided by n minus m, which is equal to -4 plus 1, and number of poles are 3, number of zeros are 1, so it is -4 by 2, which is -2. So the centroid is at -2, 0 location. Okay, very simple. Now there is another question. Find gain at the breakaway point with open loop transfer function given as k divided by s into s plus 1. So for this open loop transfer function, find out the gain at the breakaway point. How can we solve this question? First, we need to satisfy the condition at which with which the breakaway or break-in point exists, and then if that exists, for that s we need to calculate the gain. So we proceed by similar way that we have done in the previous question. GH is given as k divided by s into s plus 1, and we need to write it in the form of as by ps. So again, as is 1 and bs is s into s plus 1. Then we need to solve b dash a minus a dash b equals to 0. Okay, b dash of s, that is derivative of b with respect to s, is nothing but s plus 1, which is 2s plus 1, and since a is constant, its derivative is 0, and then we need to put it in this equation. Then we will get 2s plus 1 equals to 0, s equals to minus half. So this will be the breakaway point. Now at this point we need to find out the value of k. Okay, because we know gh should be minus 1 using the criteria of 1 plus gh equals to 0. So gh in our case is k into a by b equals to minus 1. So k is minus b by a, and we need to find it at s equals to minus 1 by 2. So b was s into s plus 1 divided by 1, okay, and minus is equals to minus 1 by 2. What value we will get? And this value should be positive also. So k will be minus of minus half minus half plus 1. So this is nothing but 1 by 4, that is 0.25. So the value of k, that is the gain at the breakaway point, is 0.25. Okay. We'll solve one last question. The root locus of feedback control system having characteristic equation s square plus 6ks plus 2s plus 5 equals to 0. So this is the characteristic equation of the closed loop transfer function where k greater than 0 enters into real access at. The root locus of feedback control system having characteristic equation enters into real axis. We need to find out at what point the root locus enters the real axis whose closed loop transfer function characteristic equation is given as this. Okay, to solve this question, first we need to figure out what is the open loop transfer function, then only we can proceed further. What is the open loop transfer function of this system? Okay, to find that, let's write the open loop transfer function in the form of k as by bs, right? Then the characteristic equation is nothing but 1 plus gh equals to 0. So 1 plus k as by bs equals to 0 means bs plus k as is 0. Now from here, can we find out the open loop transfer function now? Okay, we compare it with this one, which is this. S square plus 6ks plus 2s plus 5 equals to 0. What will be as? As is nothing but the coefficient of k, which is this term. So 6s. And what is bs? PS is all other terms which have no k. So it is s square plus 2s plus 5. Okay. So the open loop transfer function will be 6ks divided by s square plus 2s plus 5. Right. Now identify the point at which on the real axis at which the root locus enters. So we know that the root locus starts at open loop poles and it terminates at open loop zeros. So the 0 in this case is s equals to 0. So it will terminate at s equals to 0. The question is at which point it will enter the real axis. Okay, so the real axis means this part, right? So one option could be the open loop poles, but that needs to be real if the root locus is entering it. But if you solve the open loop poles, what you will get? Find out the open loop poles of this transfer function. S square plus 2s plus 5 equals to 0. This will give s at the root 4. Okay, so it is so the open loop poles are imaginary, they are not real. Okay, they are complex, they are somewhere here and here, and we have a 0 at here. So it will start from not from the real axis but from the complex plane. Then what we can do, we can think of the break it point, okay, or breakaway point. So if that is the case, then we know that it will hit the real axis at some point. Okay. So since the root locus will start from the open loop poles, somewhere it will hit the real axis. Okay, and then it will terminate at 0, one branch, and other branch will terminate to infinity. So there is some break-in point in the root locus, and through this point it will enter the real axis, right? What I am saying is, so we have a 0 at the origin and pole are complex, so it may hit the real axis such that the one branch will terminate to 0 and another branch will go to infinity. So we need to find out the break-in point for this system, and that point will the point the root locus will enter the real axis. Okay. So the problem simplifies to finding out the break-in point, and for that we know we have already find out a and b, so we need to find out b dash a minus a dash b again, and what will be b dash s? B dash of s will be, from here we can find out it is s plus 2, and a dash s will be 6. Sorry, it is 2s plus 2. Okay, so b dash into a is 2s plus 2 and a is 6s minus a dash b, and b is s square plus 2s plus 5 equals to 0. It will be 12s square plus 12s minus 6s square minus 12s minus 30. This will cancel out. We will have 6s square minus 12. Okay, sorry. We'll be having 6s square and minus 30 equals to 0. So s will be plus minus 530, it will be root 5. Okay, so we are getting 2 points, plus root 5 and minus root 5. We need to have a valid s which should lie on the root locus, and the point will lie on the root locus if it satisfies the condition 1 plus gh equals to 0, like we have seen in the earlier question, and this simplifies to finding out k, which is minus b by a, such that k is greater than 0. Okay, so we need to solve k equals to minus b by a for these 2 points, and we need to check if k is positive or not. So the k for which so the s for which k is positive will be the break-in point. Okay, so solve it for s equals to root 5. Let's solve it for plus root 5 first. Then it will be minus b. Minus b, it is minus s square plus 2s plus 5 and divided by 6s. If we put root 5, it will be minus of 5 plus 2 root 5 plus 5 and divided by 6 root 5. So both the numerator and denominator are positive with one negative sign, so it will be something negative. Okay, so k will be negative, which is not a valid point. Not okay. So then the correct option must be minus s minus root 5. So let's check k for this also. For minus root 5, it will be so it will be 5 minus 2 root 5 plus 5 divided by minus of 6 root 5. Okay, so these minus minus will cancel out, and 5 plus 5 is 10, and 2 root 5, this term will anyhow will be less than 10, so the numerator is positive and the denominator is also positive, so it will be some positive number. So it is a valid point which lies on the root locus. Therefore the root locus enters the real axis at s equals to minus root 5. This is the correct answer. Okay, that's all for today from my side. If you have any question, you can ask, or we will meet next week from 6 to 8. Thank you, everyone.